Good afternoon, engineers. I'm glad to have this opportunity to meet so many friends abroad through this online training course. I'm the host of this course. Also, I'm the marketing manager of Cinerock. My name is Donna Zhang. Hi. Welcome all the participants for this special course on low-strain PIT testing of foundation pi. Low-strain testing method is mainly used to detect the integrity of the pi. It is a relatively mature method which has obvious advantages, such as simple to use, low cost, and reliable results. So it is a powerful means to detect the pi quantity at home and abroad. The first PIT tester in China was launched in 1986, which was developed by our company. In the same year, we also registered the RSM brand. So far, our RSM Pi integrity tester has a history of 36 years. Over the past 36 years, the products have been continuously improved and innovated, and a variety of types of pi dynamic testing instruments have been developed, which have been widely used in major engineering tests at home and abroad. When learning the low-strain testing method, we should understand the testing principle, application range, how to select a vibrating hammer, and learn how to read and analyze the testing waveform. Now, today's course will last about 2 hours. The course is divided into 4 parts. The first part is to explain the principle of low-strain testing, on-site testing method and technology. The second part is to share some PIT theoretical curve and explain how to analyze the curve. The third part is to introduce the operation process of RSM-PRTR low-strain pi integrity tester. And the last part is to share some typical cases of PIT testing. And I hope today's course can give you a more systematic and intuitive understanding of PIT testing. Welcome again, all the students. I really hope you can get something from today's course. Now we will enter the formal class. The course is low-strain integrity testing technology. It will last about 30 minutes. If you have any question during the course, you are welcome to send your question in the chatting box, and our teacher will answer your question in the rest time.
Welcome to Synarock Low-Strain Pile Integrity Test Training course. This section of the course mainly talks about low-strain pile integrity testing technology, which is more theoretical. I will explain PIT testing from the following 6 aspects. 1. Concept of stress wave. 2. The laws of stress wave propagation. 3. Scope of application for PIT. 4. Pile integrity tester. 5. Sensor. 6. Hammer impact. The first part is the concept of stress wave, which is the most basic principle of low strain, and explains why we use low strain method to test the integrity of the pile body. How does the stress wave come into being? When a disturbance suddenly occurs in a certain place of the medium, the deformation caused by the disturbance will spread along the medium from near to far. This phenomenon of disturbance propagation is called stress wave propagation. The interface between disturbance and undisturbed is what we call the wave front. When the stone is thrown into the water ripple slowly spreads out from near to far. So the part of the ripple vibration is the disturbed surface, and the part without vibration in the distance is the undisturbed surface. The wave speed of stress wave refers to the propagation speed of this disturbance. What are the characteristics of stress wave? In the process of propagation, generally, there are reflection, transmission, scattering, superposition, dispersion, and other phenomena. First look at refraction, reflection, and transmission. When the stress wave enters another medium from one medium, the direction of propagation will change, due to the different propagation speed of the stress wave in different media, which is called refraction. When the stress wave propagates to the interface, where the impedance of 2 media changes, a part of the stress wave will be reflected from the interface to form a reflected wave. The other part will cross the interface and enter another medium to form refracted waves. Transmission occurs when it is perpendicular to the impedance-changing interface of 2 media. In addition, stress waves also have the law of superposition. That is, when 2 trains of waves meet in the process of propagation, the 2 trains of waves will maintain their original characteristics, such as frequency, wavelength, amplitude, and the vibration direction of particles, including the direction of propagation will not change. But the superposition effect of stress waves will occur in the area where they meet. That is, the vector superposition of vibration caused by 2 trains of waves alone at this point. We just talked about several laws of stress wave. Next, let's look at what is one-dimensional stress wave. One-dimensional stress wave involves wave impedance. What is wave impedance? It is the ratio of the increment of internal force on the cross-section of the member to the increment of particle velocity. In other words, it is the force value required for the particle to change its speed by a unit speed. Then, according to the above definition, let's look at the following formula. The change of force can be converted into the cross-section multiplied by stress, which is a relationship between elastic modulus and strain. So the classical formula of wave impedance is derived finally Z equals rho Ca. Rho is the mass density. C is the elastic wave velocity. That is, the wave velocity of stress wave propagation just mentioned. And A is the cross-sectional area of the member. Therefore, from these aspects, the magnitude of wave impedance is determined by the properties of materials. Through derivation, we can get the relationship between particle velocity and strain. Particle velocity is equal to strain multiplied by elastic wave velocity. So what is the relationship between particle velocity and stress? We all know that strain is stress divided by elastic modulus. So we deduce the second formula from the above formula. Then it is transformed into the relationship between particle velocity and force. The stress is obtained by dividing the force by the area. So the three formulas can be derived. Generally speaking, when we do experiments or tests, when the stress wave propagates from medium 1 to medium 2, the direction of stress wave propagation is often perpendicular to the interface of the two media. So when the wave impedance of the two media is different, the stress wave will reflect and transmit at the interface. And the reflection and transmission are closely related to the change of the wave impedance of the media. When the rod top is knocked, we can obtain the propagation law of stress wave in the rod by analyzing the speed response of the rod top, the distribution of the difference of wave impedance in the rod body can be determined by the variation characteristics of the velocity response time history curve. According to some formulas we derived above, we can directly relate the reflected wave velocity to impedance and incident wave velocity, including the relationship between transmitted wave velocity and incident wave velocity and impedance. That is, the reflected wave velocity is equal to the negative incident wave velocity, and then impedance 2 minus impedance 1, divided by impedance 1 plus impedance 2. The transmitted wave velocity is the sum of the incident wave velocity, multiplied by twice the impedance 1 divided by impedance 1 plus impedance 2. Let's take a closer look at the laws of stress wave propagation. We have seen some laws of stress wave propagation in the rod. So how to introduce the stress wave into the low-strain integrity testing of foundation piles? We need to make some assumptions about the foundation pile. First, the pile body is one-dimensional, continuous, homogeneous and linear elastic. That is to say, the material is uniform and equal in cross-section, and the cross-section of the stress wave in the deformation of the pile body remains plane and parallel to each other. That is, plane wave. The stress is uniformly distributed on the cross-section, ignoring the lateral inertia effect of the pile body. In addition, the influence of the soil around the pile on the pile body and the influence of the pile-soil coupling surface are ignored. Then we will talk about the concept of pile integrity. Pile integrity is the relative change of pile section size and the combination of pile material compactness and continuity. What is the relative change of section size? How can we relate it to wave impedance? The relative change of section size is the change of A. And the compactness is. Continuity is the change of C. Whether it can effectively propagate is actually a comprehensive indicator of whether the wave impedance is uniform. What is the definition of pile defect? It will deteriorate the integrity of the pile body to a certain extent, causing the reduction of the structural strength and durability of the pile body. Generally speaking, we often encounter that the pile body is broken, and there are cracks, shrinkage, mud and debris, cavities, honeycombs, looseness and other undesirable phenomena in the pile body. Pile defects are a general description of this phenomenon. The low-strain method is a testing method that uses low-energy transient excitation at the top of the pile, measures the velocity time history response curve at the top of the pile, and evaluates the integrity of the pile body through time domain analysis or frequency domain analysis of wave theory. In the figure on the right, the stress wave generated by low-energy transient excitation at the pile top propagates along the pile body, and the stress wave meets the discontinuous or defective position in the pile body to generate a reflected wave. We receive its signal through the sensor installed on the pile top, and then analyze the phase amplitude and other indicators of this signal through the stress wave method, and then analyze, judge and evaluate the integrity of the pile body. This is the detection principle of low-strain method. Low-strain PIT testing is not suitable for all integrity testing, and has a certain scope of application. In some cases, low strain will have a good testing effect, while in some cases it is impossible to judge. Let's take a look at the scope of application of the low-strain method. The low-strain method is applicable to detecting the integrity of the pile body of concrete piles, and judging the degree and location of pile defects. But it can only be judged qualitatively, not quantitatively. The theoretical basis of low strain is the model of one-dimensional linear elastic rod. Therefore, the ratio of the slenderness ratio of the tested pile, the pulse of transient excitation, and the wavelength of the effective high-frequency component to the transverse dimension of the pile should not be less than 10, which is the requirement of one-dimensional linear elastic rod model. In addition, it is also required that the designed cross-section of the pile body should meet the basic rules. The one-dimensional theory also requires that the assumption of plane section is valid when the stress wave propagates in the pile body. Therefore, for special-shaped piles, such as thin-walled steel pipe piles, large-diameter cast-in-situ thin-walled concrete pipe piles, and steel piles similar to H-shaped piles, if we use the excitation response to receive on the top surface of the pile, the low-strain method is not applicable. Let's look at some common defects. What are the common defects of cast-in-place piles on the construction site? Honeycomb: the whole pile is loose. Some part of the pile body has mud inclusion and diameter reduction. The pile body has cracks, the pile is bent due to hammering, poor quality or other reasons, as well as the latents on the top surface of the pile and some sediment on the bottom surface of the pile. What are the common defects of precast piles? The quality of pile connection between multi-section piles, The fracture during pile driving. Cracks, horizontal or vertical cracks. The condition that the pile body is damaged by hammering. The pile body is not smooth, and the pile body is loose during prefabrication are common. We analyze these defects as quality problems. Segregation, mud inclusion, latence, sediment and looseness will all cause density reduction. The reduction of diameter, holes, cracks, including joints, will cause the reduction of cross-sectional area. The fracture of pile body can be considered as the cross-sectional area is about 0. These defects, except the expansion, will basically cause the wave impedance to decrease, and the expansion will cause the wave impedance to increase due to the increase of the cross-section. According to these, we can know that most defects are wave impedance reduction. As we have said before, for the pile with reduced wave impedance of the pile body, the reflection in the same direction will occur at the location of the defect. Can we deduce it backwards? It is actually very difficult to judge the nature of the defect of the pile body according to the reflection in the same direction. If the nature of the defect is to be judged, it should be comprehensively analyzed in combination with the geological construction conditions, or verified by excavation, core drilling, acoustic transmission and other methods. Therefore, it is suggested that when you issue the report, you only state the defect and its degree, not the specific defect, because without verification, it is difficult to accurately analyze the nature of the defect, and sometimes we are faced with the combination of multiple defects. We can make some conclusions about defects. Piles with serious defects generally produce multiple reflections, so it is not easy to find the reflection at the bottom of the pile. That is, it is difficult for the stress wave to transmit downward at the location of the defect. Therefore, it is recommended that when you issue the report, you only state that there are serious defects at the location of the defects, and do not easily judge it as fracture. I will give you an example in the detection technology section. When the wave impedance of the pile body increases, some reverse reflections will occur at the corresponding positions. Most of the piles are mainly under pressure, so the increase of wave impedance is helpful to the bearing capacity. Therefore, in practice, it is recommended that you do not evaluate the piles with increased wave impedance when issuing the report. Next, let's take a look at the identification ability of low-strain PIT method for defects. What defect can be identified? The pile bottom changes greatly, and the impedance changes greatly due to mud inclusion, cavity, break, segregation, bulging, necking, soil layer change, and material change in the pile body. The defects that can be identified on the left have obvious changes in wave impedance, and those on the right are more difficult to identify, such as thinning, thickening, bending, small defects and pile bottom sediment. The first one that is difficult to identify is the gradual process of area wave impedance. The low-strain PIT method can test some abrupt phenomena, rather than gradual phenomena. Gradual changes are difficult to reflect in low-strain PIT test. The second is a small defect. The key is whether the size of the excitation frequency can distinguish this defect. The sediment at the bottom of the pile is also a defect that cannot be identified with low strain. Previously, we introduced the principle of low strain testing to you. Now let's take a look at the low strain detection system. The current PDA testing instrument, no matter which specification, is basically attributed to the relevant provisions of the current industry standard, ASTM D5882-16. What are the RSM series low-strain PDA devices of Synarock? In the figure below, RSM PDT-D high-strain pile bearing tester is on the left. RSM PRT-P low-strain pile integrity tester with dual channel is in the middle, and a single channel, RSM PRT-R low-strain pile integrity tester, is on the right. What types of sensors are common in low-strain testing? What are the requirements for sensors in low-strain testing? We should try to choose sensors with wide range, high resonance frequency, good damping characteristics, wide frequency response range and high sensitivity. High frequency with narrow pulse signal is often used for signal recognition of shallow layer measurement, and it is not suitable to use speed sensor. In addition, it must be noted that the sensor should be set according to the metrological identification or calibration mechanism, because the moving speed of the particle is converted through sensitivity. What kinds of low-strain sensors are commonly used? The black cylinder on the far left is a speed sensor with high damping and short residual vibration. The middle one is a low-strain charge type acceleration sensor, used in some very old equipment. This sensor must be designed with a charge amplifier in the instrument in order to convert the charge signal into an effective electrical signal for analysis and processing. The low-strain piezoelectric acceleration sensor on the right needs to supply pressure to the sensor, but the electrical signal needs to be transmitted to the instrument after processing. So there is no need to equip the instrument with a charge amplifier. I put the speedometer and accelerometer here and made an index comparison. From the perspective of weight, the speedometer is heavier and larger, so the resonant frequency speedometer is low, and its amplitude frequency characteristics, phase frequency characteristics, including sensitivity, are worse than those of the accelerator, including the test frequency band. So from the actual effect of the test, we have some general understanding. If we use a speedometer to measure the velocity time history response curve, its oscillation is relatively strong, and the shallow defects are not obvious on the signal curve we collected. However, because the accelerometer collects the acceleration signal, it can only be transformed into the velocity time history response curve we want to analyze through integration. Coupled with its good performance, the oscillation seen on the velocity time history curve is relatively weak, and the response to shallow defects is relatively obvious. This is also the reason why it is recommended to choose high-sensitivity accelerometers as much as possible when testing the low-strain reflected wave of foundation piles according to various specifications. There are several types of hammering impact. What requirements should excitation equipment meet? The equipment for transient excitation shall include force bars, hammers and hammer pads that can excite wide and narrow pulses. According to the test purpose, the wide pulse is mainly aimed at the pile bottom, and the narrow pulse is mainly aimed at the shallow defects of the pile body. So it is necessary to equip with corresponding appropriate force hammers, force bars or hammer pads. However, the hammer and hammer pad need to be selected through field experiments. The choice of hammer is not only related to the pile, but also related to the soil around the pile and other geological conditions, whether the stress wave meets the requirements, and whether it can spread to the bottom of the pile. Does not have a very empirical law, so it can only be evaluated and judged through field experiments. There are several types of hammers. On the far left is a combined hammer, which can be turned into a force bar or a hammer. Different frequency responses can be obtained by matching different hammers. In the middle is a hammer. Different frequencies are obtained according to different hammers on both sides. On the far right is the hand hammer of the accelerometer installed on the hammer. It can't be very big, because its main purpose is to measure the defects of the shallow part of the pile. So it's not necessary to use a big hammer to test. Mainly for the transient response method test of the dual-channel low-strain instrument.
Now the first part of the course is over. We have sent a sign-in link in the chatting box. You need to sign in and we will issue a certificate who have been signed in our course. Just to emphasize, sign-in means you have been participated in today's course. So if you want to get a certificate, you need to sign in. Now we will have 15 minutes rest. After 15 minutes, our class will continue. The next course is low strain PIT theoretical curve analysis. See you later. Hello everyone, welcome back. Now we will enter the second part of today's course, low-strain PIT theoretical curve analysis. In this part, our teacher will explain what wave impedance is and how the change of wave impedance affects the low-strain detection waveform. If you have any question during the course, you are welcome to share your question and we can have more discussion together. Now the clock